Of course, when I told you. Okay, so it's 2 o'clock. Howdy. 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 Again. Howdy. 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 Okay, it's 2 o'clock. It's time to get started with the lecture. If you have your homework, please pass your homework to this side of the classroom. Yeah. Okay. Any questions about the material we covered last time? Anyone remember what we started covering last time? We covered, or we started the topic of 1 and 2 self-automation problems. And specifically, we talk about estimation and also costing interval. Okay? So today we're going to start from there, and I'm going to start with a problem that I studied when I was an undergrad. This actually was a real problem. And what I'm going to show you is just a solution. It is a simple problem, but I think it's going to give you some intuition of why the information we are studying at this point of the class is important. So if you have your homework, you can submit it at the end of the lecture. The other thing is I have your previous homework graded, so by the end of the class you can pick up your last or the previous homework. Okay, so this is the problem I was referring to. Again, a very simple problem. Here we have some customers arriving at a counter with an exponential arrival times of 10 minutes. And we have 2 clerks that accept and check the orders and process payment using separate lines. So what we had at that point was 2 clerks. Let me make a very simple drawing here. So we had 2 clerks, and they were taking care of the customers on separate lines. Okay? And then a recommendation was made to select their next activity from a single FIFO first in, first out queue. So basically what the manager wanted to test is if the system, instead of having two separate queues, if we had only one for both, and how would that affect the system? Would that improve the system performance or not? That was the question. Again, very simple question. We have 2 queues, 2 separate servers. And you wanted to know if you have only one queue to select the customers for the same 2 clerks, would that affect the system performance? And for the system performance, what we were looking at was the average time for the customer in the system. So this is what we started doing. We developed a simulation model for the real system, which was this one. And we ran some experiments. We also collect information from the system, from the real system, about the time that the customer spent inside the system. And then we built a simulation model for the second system. And here were our preliminary results. So for the system with 2 lines, we found that the confidence interval for the average time was this. So where some customer were waiting was from 10 to 15 minutes on average. So the confidence interval was telling us that the actual population mean was within these two bounds. And for the second system, we found that the bounds were a little bit higher, from 12 to 17 minutes. So what I'm saying, what I'm trying to show you here is, this is our first system, this is our second system. So for the first system, we had this, this is 9 to 15. And from the second system, for the second system, we had something like this, 12, 17. So this is what we found initially. And my question for you is, based on that, this is the confidence interval for the first system. And let's see, this is the confidence interval for the second system. Based on that information, what will be your recommendation? And again, this is the waiting time of the customer. So you're trying to minimize the waiting time. First or second system? Why is that? Shorter waiting time? Waiting time? Okay. That's a good answer, but it's not correct. And to explain why, we need to understand what a confidence interval is. And that's why I'm bringing this example. From our discussion last time, what we were saying is that the confidence interval tells you or gives you some bounds to basically limit with a percentage of confidence or a probability that the actual population mean is within some bounds. So for this first interval, what we are saying is that the actual mean, the actual waiting time for the customers is within these bounds. So it could be here, it could be here, it could be here. Also, for the second system, it could be here, here, here. So something that can happen, and we don't know, is that the actual population mean for this system is here, and the real population mean for this system is here. So that will give you a different answer. Because if that is true, that means that the waiting time for the second system is better than the waiting time for the first system. So based on this confidence interval, you cannot make any decision, because you don't know where the population mean is. Okay? So in order to make a decision, you need to gather more information. You need to get more samples, increase your size, your sample size. So in some way, if you increase your population size, at some point you should be able to have two confidence intervals that do not overlap. And if you get to that point, then you know that the systems are different and one is better than the other. But with this type of information, you cannot make any decision. You understand why, right? Is that clear? So that's why we use confidence interval, because we are only basing our decisions on samples. We are not studying all the population. So if you construct some confidence intervals for these statistics, you also have to make sure that your confidence intervals do not overlap if you're trying to compare them. If they do overlap, then there's no way that you can tell that one is better than the other, because the population mean is somewhere within those bounds. Okay? So that's a real problem example. Again, very simple, but give you some intuition about how this information and these techniques are used. Okay? So from there, I don't think you have this slide. I can post those this slide after the class. But the important thing is that you understand what I'm explaining. And for sure, gonna have at least one question in the exam basically asking about this. So make sure that you understand. Okay? Because techniques are important, but the most important thing is that you understand how you can use it. Okay? So if you still have questions, let me know after the class. We can discuss this one more time. Okay, so we're going to start from what we left last time. So we covered statistical inference and classical method of estimation. Today we're going to cover the last 6 topics, hopefully. So we're going to start with the single sample estimating the mean. And these are the objectives. We covered this last time. But again, I want you to be able to construct confidence intervals for the mean and also for the variance and for the population proportion, and also be able to construct some prediction intervals. Okay, so last time we covered the two-sided intervals, confidence intervals. Today we're going to talk about one-sided confidence intervals. And there are many applications in which only one confidence bound is important. If you're looking for to satisfy a lower bound requirement and so on. For example, if the measurement of interest in tensile strength, the engineer received that information for a lower bound only. These bounds can communicate the worst case scenario. So in that case, you only need one bound, which is the one corresponding to the worst case scenario. So one-sided confidence bounds are developed in the same fashion as the two-sided intervals. So here is the description for one-sided confidence intervals. And again, this is assuming that you know sigma squared, which is the variance of the population. So another question I had this morning from one of the students is, when you use T or when you use Z? C values comes from the standard normal distribution, and you use confidence intervals with the C values when you know the population values. So if you have that information available, if you want to construct some confidence intervals, then you can use the bound using the standard normal. Okay? If you don't know the information about the population variance, then there are use some other confidence intervals that use the T distribution. Okay, but for now, we are assuming that we know the variance of the population. So the one-side confidence bound for the upper bound is just the sample mean plus Z value of alpha times the standard deviation divided by the square root of n, and the lower bound is the subtraction. So, as an example, let's look at this problem. So in a psychological testing experiment, we have 25 subjects are selected randomly, and the reaction time in seconds to a particular stimulus is measured. Past experience suggests that the variance in reaction times to this type of stimulus is 4 seconds squared. So this should be seconds squared. Excuse me. So this problem is already telling you that population varies. So based on that information, you know that you can use the confidence intervals where you know the population variance, which is the one that we discussed, using the standard normal. So here you know the variance, and you also know that the average time for this subject is 6.2 seconds. And the question is, give an upper 95% bound for the mean reaction time. Okay, so we know that the upper 95% confidence is given by this. So the sample mean plus the standard normal value for alpha, the standard deviation divided by n. So again, we know the variance, we can use the standard normal distribution. So what information we have the sample mean, which is 6.2 seconds. We know the population variance, so that's why I'm using sigma squared. Bless you. And we know the sample size, which is 25. We are looking for a upper bound with 95% confidence. So we know that 0.95 is going to be equal to 1 minus alpha. So our alpha is 0.05. And we need to find the value of the standard normal for that alpha. So if you have your standard normal table, what you do to find that number is to go inside the table and find 0.05. So you go inside the table, and then you need to find out what's the value of z that will give you that number. So in that case, that number is 1.645. Okay, so now we have all the information we need. So this is going to be 6.2 plus 1.645 multiplied by the standard deviation, which is the square root of 4 divided by the square root of 25, and that is 6.858 seconds. So the difficulty in this topic, first, is identify what information do you have from the problem. So if you know the variance, and you know that the variance is coming from the population, you can use the confidence interval using the standard normal or the c-value. Now, if you don't have that information, then I'm going to show you some other techniques that you can use to construct confidence interval. But for now, we are assuming that we know the standard deviation from the population or the variance of the population. The other difficulty is how to find these values from the table. You need to be sure that you're using the right number, you're finding the right number from the table. And the last thing is how to interpret the bound or the confidence interval. Yes, sir.
Is that the Z chart? Are we using T distribution or which one is it? Z normal?
Z is normal 0, 1. The standard normal distribution. Yeah.
It's like the first table.
Right, yeah, I don't see any values that are 1.
That equals this number. Remember, these numbers are the column and row, top row and column.
Oh, that's right, yeah, you do.
Okay, so what you do is you find 0.05 from inside the table. Make sure that you practice how to get those numbers. Okay? It's not straightforward. Yes?
Is the negative not matter?
Yes, that's a good question. So the way we use the probabilities is based on alpha, but in reality what you're finding is the 95% probability because you want your confidence to be 95%. So what you remember the standard normal distribution. So what we have is this. And this is a symmetric distribution where the mean is 0. And if you say that you want to have, let's say, 1.65 here, 64.5, that's your C value. That C value corresponds to this area. And that area is 95%. Okay? The value of alpha, on the other hand, this is 0. 1.645. So this probability is just this area, and that is the value, this value, 0.05. Negative 1.645. So the way to see it is you are actually looking for the 95%, so you can go straight to the table and find the 95% and get that number from the table, or you can find the value of alpha and change the sign to positive. It's the same thing. Remember, the probabilities are symmetrical. Any other questions? Okay. So now we are moving to the next case. And this is the case in which we have the standard deviation is unknown. So we don't know the information from the population. Okay, so the case on which we have the standard deviation that is unknown. So frequently we must attempt to estimate the mean of a population when the variance is unknown. So we don't know anything about the population, and we're gonna base our confidence intervals from the information we get from our sample. Okay? So in order to do that, we need to remember our chapter in sampling distribution. So when you were dealing with the estimation of the variance, you remember using this random variable t. And we're going to use t to construct our confidence interval when we don't know the sample, the standard deviation of the population. Okay? So from a random sample, from a normal distribution, this random variable has a student t distribution with n minus 1 degrees of freedom. So t can be used to construct a confidence interval on the population. So the only thing you're going to do is to change or to replace the standard deviation of the population with the standard deviation of the sample. Okay? So in that, we'll have a t distribution. So this is a new confidence interval again. When you use this confidence interval, you need to be sure the case that you're looking at. So for this one, we know the population mean. Excuse me. We are constructing a confidence interval on the population mean, but we don't know this, the variance of the population. Okay, so for those cases, we have the confidence interval that is based on the t distribution. So the other assumption that we're making is that the sample mean and the sample standard deviation is coming from a normal with unknown variance, and we can construct that confidence interval using this expression. Okay, and remember, for the t distribution, we have to deal with the degrees of freedom. So you need to take into account the sample size and computing the degrees of freedom. So the degrees of freedoms are the sample size minus 1. In the same way, we can compute the confidence intervals for just one side. So the one-sided confidence intervals are basically the upper bound when you add this standard error to the sample mean, and the lower bound is just a subtraction of the standard error from the sample mean. Okay? And the t alpha value is the t value having an area of alpha to the right of the curve. So let's look at this example. So the contents of 7 similar containers of sulfuric acid are 9.8 up to 9.6. So we have 7 observations for this sample. and we are asked to find the 95 confidence interval for the mean contents of all such containers, assuming that they are approximately normal. Okay? So as you can see in this problem, we don't have any information about the population. The only information that we have is these numbers, and they're coming from a sample. And your sample size is, what's the sample size? 7. Okay? So we're going to use this information to construct a confidence interval. So what will be the first thing you'll do? Correct. So you're going to have to find the sample mean. So X bar is very simple, is 9.8 plus 10.2 plus all those numbers up to 9.6. And this is divided by 7. So this equals 10. Okay? What is the second thing that you need to find? Say that again. The sample variance, correct? So, to get the sample variance, or you know that this equals 1 over n minus 1 times the summation from I to 1 to n of xi minus x bar squared. And again, I have repeated this several times. You need to make sure that you understand how to compute the sample value. Okay? I've seen this error multiple times. Students missing points on the answers because they don't know how to compute the sample variance. Okay? So make sure that you know how to solve this. So if you find the sample variance, that will be equal to 0.283. So now we have the sample mean and the sample variance. And again, we are doing this because the variance of the population is unknown. If you know the variance of the population, you don't need to compute the sample variance. You just use the confidence interval for using the standard normal distribution or the z values. Okay, so now we have this. So we can compute the confidence interval. So for mu, we have this. The upper bound is just x bar plus the t value of alpha divided by 2 times the s divided by the square root of n. And for the lower bound is just the same thing, minus t alpha half s square root of n. Okay, the main difference again, we are using S instead of sigma, and we are using T instead of Z. And that's why now we need to find out what is the alpha value that we need. So we have a 95% confidence interval. So our alpha is 0.05. So alpha half is 0.025. And now, yes?
So when do you divide the alpha by 2?
It's based on the type of confidence interval that you're looking at. So in this one, we are using the two-sided confidence interval. So on those cases, you have to use alpha divided by 2. When you have only one-sided, you don't have to. Okay? Good question. So now instead of using the Z table, you have to use the T distribution, right? So from the T distribution, that is table A4 from your textbook. From that table, and we practice how to use that table in class. From table A4, we can get that T of 0.025 equals 2.447. And This is using how many degrees of freedom? 6. Okay, so you need the alpha value, and you need V equals 7 minus 1, which is 6. So we have the information. Now we can compute that confidence interval. So I will write that here. So we're going to have mu greater than 10 plus 2.447 times 0.283 divided by the square root of 7, and mu less than 10. Oops, this should be yes, this is invert. Yeah.
Also, shouldn't be a x square root of
Yes, should be the square root of s. 1 second. So this should be the square root, and this is minus, and this is plus 2.447 times the square root of 2.283 divided by the square root of 7. And this is equals to mu. The upper bound is 10.26 and the lower bound is 9.74. Okay, so once you identify the information you have and you know what confidence interval you want to construct, the next thing is just plugging in the numbers in the formula. Okay, so the important thing is see what information you have in hand, identify the parameters you need to compute, find those, then get the information from the table and plug in those numbers. Yes, sir.
That's what a little confusing. That's square. Yeah, no, it's like 5.319. We would change those answers.
Oh, so this is not the right.
If that's s squared, it's s.
That's S or
Is that s or s squared?
yeah, I'm sorry. Let's see. So this, yes, this should be S. I need to double check. So you found the standard deviation of the sample and was 0.283.
Yeah, it's like 0.08 thickness per that. So the variance is.
Yeah, so this is the standard deviation. Okay, sorry. So that's the standard deviation, and this shouldn't be the square root. Yeah, so let me rewrite this really quick. So this is times 0.283, and this is 282. Okay, thank you. Any other questions? So I was saying, find out what information you have in your problem, identify the confidence interval that you want to use, find the parameters that you need to compute, get the information from the table, and plug in the numbers. Okay, so let me see if you can get some intuition from these formulas. So let's see. You have a confidence interval here that is about less than 1 unit, right? If you want to decrease the size of this confidence interval, what would you do? Yeah, it has to be with the sample. Look at the formula. So it has to be with the sample. Yes. So if you increase the sample, you will reduce the size of the confidence interval.
In this case.
No, it is always true.
Well, yeah, any of the ones where you don't know the variance.
Yes. And think about the real life problem. If you have more information about the system, that means that you can have a better conclusion about the system. If you only pick 2 points out of 100, you're basing your conclusions on only 2 units. But if you capture the information of 50, for instance, you'll get more information about the system, so you will be more sure about the actual mean or the standard deviation of your system. Okay? So if you want to decrease the size of the confidence interval, then you need to increase the number of observations that you're collecting from the system. Think about this. So, while we were at the beginning of the lecture, so this was a problem. We didn't have enough information from the system. We got more information about the system. We were able to close those intervals in such a way that they did not overlap anymore. So we were able to make a final decision and conclusion about the system. Okay? So there's another important fact about intervals. So if you want to decrease or reduce the size of your confidence interval, you need to increase your sample size. Okay? Questions? Okay, so a question for you. If you want to decrease the size of the confidence interval, what would you do? The size of the confidence interval?
My whole lifeline.
The only thing that you can do is to increase the sample size of your experiment. Okay?
You could also increase alpha.
Increase alpha, yeah, but you're gonna change the confidence. You don't want to change the confidence of your experiment. Okay? Questions? Okay. So now we're going to explain another concept about confidence intervals, and this is the concept of a large sample confidence interval. So when normality or the normal distribution cannot be assumed, the population sample the standard deviation of the population is unknown, and the size of your sample is greater than 30, then you can replace the standard deviation of the population with the standard deviation of the sample. Okay? And that will give you a confidence interval of this type. So now you're using Z, but you're using the sample variance and standard deviation to compute your confidence interval. Okay? So first thing we saw was confidence interval with the Z value of the standard normal and the population of the standard deviation of the population. Second confidence interval, we're using the T distribution with the sample variance. Now we're saying that if normality cannot be assumed and we don't know the population standard deviation and n is greater than 30, we can replace sigma in the confidence interval. So we're going to have a different type of confidence interval. Now we can use Z, the standard normal, with the sample standard deviation. Yes?
So is that assuming because of point 1 that normality can't be assumed but the sample interval doesn't apply?
It is basically assuming that the central limit theorem applies because you're having a large sample size and we are using the same constraint.
This is the basic assumption, simple belief there on the fact that the larger n
Mhm.
more likely normal
Yes, yes, but on the other two confidence intervals, we were assuming that we knew that the observation were coming from a normal. Now we don't know. So normality is not assumed. Okay? So this is only an approximation, and the quality of the results becomes better as the sample size grows larger. Okay? So in order to apply this, let's look at this example. So we are looking at the SAT mathematics course of a random sample of 500 high school seniors in the state of Texas. And the sample mean and standard deviation are found to be 501 and 112. And I want you to find the 99% confidence interval of the mean for the scores in the state of Texas. Okay, so we don't know if this is coming from a normal distribution. Okay, but we know the sample mean and standard deviation. Okay, so we also know that the number of observations is high, is 500. So we can use the approximation to compute our confidence interval. So X bar equals 501. That's our sample mean. And again, let me make a note here. So since the sample size is large and equals 500, then we can use the approximation. And the approximation is X bar plus minus the value for alpha hat of the standard normal times S divided by the square root of n. Okay, so we want to compute a 99% confidence interval. So our alpha value is 1%. So alpha half is 0.005. And if you find that value for the standard normal distribution, you get the positive value of that. It is 2.575. So now you have all the information you need to compute the confidence interval. This is 501 plus minus 2.575 times 112 divided by the square root of n, which is 500. Okay. So again, this is an approximation, and we are basically combining the first confidence interval we studied with the second one, and you know when to use it based on the assumptions. Okay. So we have three confidence intervals up to this point. One in which you know the normal. We have the population variance. One in which we don't know the population variance, and one in which we are using an approximation when n is large. Okay, so now I'll give you an opportunity to practice. This is a lab based on what we have discussed in class. So you can work on groups. No, so I'll give you 10 minutes to work in this.
All right. Oh, he gives us the secret.
I'll start doing the thing.
Okay, that doesn't mean that you're gonna use that, okay? In fact, you're not using this approximation in that problem, okay? And if you look at the paper, you have two pages. The second page has the tables that you should use.
X bar minus. So you find the t, we have the alpha. And we have you have 3 equals or 15.4. Yeah. 18.5, 7.9, 12.7, 11.9, 12.4, 11.4, 14.9, 17.6, 15.7, 15.8, 19.5, 8.8, 15.6, 12.9, 11.9. Okay, 347. Yeah, that's on the deck. Yeah. Not 6.
Yeah. No, it's.
Yes.
Yeah.
Yeah, there's one of it.
Yeah, just people are so much nice. I don't know.
Well, one sample, one is assuming it does.
Yeah.
Did you read this?
That's actually 3.5 on. Yeah.
They're going out by.
Yeah.
So now we use the chart. We have alpha, and the degrees are
22 minus 160.
Yeah. I think we might not have needed that. Oh, yeah, we do. We do. Yeah, we need it.
Yeah, it's the second last.
Let's do that.
Go for the export. I keep trying to put it in the export.
Do it, Ross.
Standard deviation, that's the simple right?
This is the values of the envelopes. And you don't know that.
Okay.
But this doesn't have to be, you don't relate to this.
Okay, that's the calculation.
Yeah. So what I'm expecting for the second question is just a sentence.
Okay.
That's what I got.
Okay, what's it? So you.
Mine's not much better.
Yeah, I don't think anybody's is. Nobody's good. Let me write. Divided by 21.
Yeah, he's like, no, not yet.
No.
Oh, okay, so if you do.
If we export plus minus z alpha, z alpha, your signal.
Yeah.
Yeah, what is it? It's not alpha.
I guess it is
Oh, well, that's near to be this way, it would be export of the alpha signal.
Yeah, oh, it's not.
Yeah, you're right. That's probably it. Yeah.
Yeah.
But it is alpha. Like I said, I don't have the notes.
And again, the table is on the second sheet of the answer sheet. The table that you need to use is with the paper.
This is cute.
Too slow. Yeah. Where do you think?
I just. Wait, good. Okay.
Yeah, you're right. You got it. No, it's
Oh. Yeah, I don't think it's gonna matter. We're talking about balance.
yeah, but remember this one, signal.
Oh, that's why. That's why.
This is signal.
Hey,
Yeah, but I think.
Okay, cool.
Yeah, only because
And the second question is just asking if you were using a confidence interval of one type, would you change the confidence interval type if you knew the value of the variance of the population? What would you do different? Would you use the same confidence intervals or you would use a different type?
There's 3 different types. It wouldn't be 6 types.
So, you were saying alpha were two-sided.
So, I always say that
Assume that it's the same type of problem. What would you do? Would you use the same confidence
What we do is we don't have.
Okay, 2 minutes.
Y'all look at it.
Yeah.
I gotta find my cable. That's a hassle.
Okay, how many of you need more time? So I'll give you 1 more minute.
No.
Is it okay if I have the table?
Yeah, you can keep it.
Oh, yeah.
My hair doing well.
Ready to sign up?
I don't think it's ever passed from COVID yet. No, I don't think it is. We could go. Oh, wait. I was pretty sure I
At the
did.
end. Okay, you can start passing your papers to the right side of the classroom.
I got it. It doesn't have a
Hey, first, you want to? Any other groups?
Well, I had my dad.
Okay, so let's discuss the problem, and I'll post the problem with the solution after the class as well, so you can have a copy. So the first thing you need to do is to find out what information you have, and let me see if I can. Okay, so for the purpose of the problem, you don't have the information about the population variance. So that's the first thing you need to notice. So you're gonna use the information from the sample you collect to compute your confidence interval. So in that sense, you are using the confidence interval with the t distribution. So if you find, oops. X bar should be equal to 13.71, and if you found the standard deviation, it should be equal to 3.55. Okay, so you need to find a 95% confidence interval. So the value of alpha is 0.05 and alpha half is 0.025. So the t value for this problem is t of 0.0 with how many degrees of freedom? 21. So that value is 2.08. So to find the confidence interval, then you just plug in those numbers here. And that equals mu within 15.28 and 12.14. Okay. So the second question was asking what would you do different if you know the population variance? Well, in that case, then you use a different confidence interval because you know the population variance, so you can get the population standard deviation and use the confidence interval using the standard norm. Okay. So any questions? Okay, so still have some time, so I'll cover the next topic, which is basically defining something that we already know, This is called the standard error of a point estimate. So essentially consider the estimator of the population mean, which you know is the sample mean, with the population standard deviation known. We indicated earlier that the measure of the quality of an unbiased estimator is the variance of the estimator. In this case, is the variance of the sample mean, which you know how to compute it, which is sigma squared divided by n. Okay, so the standard deviation of x bar, or the standard error of x bar, is the variance. I'm sorry, is sigma divided by the square root of n. The standard error of an estimator is actually its standard deviation. So for x bar, the computed confidence interval limit is this one. You know you're using the standard normal distribution, and this can be written as this same expression times the standard error of x bar, which is essentially this. Okay, so that's what we call the standard error, is the standard deviation of the estimate. So the width of the confidence interval on mu, which is the population mean, is dependent on the quality of the point estimator through its standard error. Okay, so in the case where sigma is unknown, the sampling is from a normal distribution. We can replace the standard deviation from the sample with the standard deviation of the population. And the estimation of the standard error will involve that standard deviation of the sample. Thus, the confidence limit on mu will be based on the t-distribution with the sample standard deviation. Okay, so same concept, just adding a definition. The standard deviation will become the standard error of the point estimate. Okay, so I think I'll start here next time. Have a wonderful weekend, Thanksgiving weekend. I have your homeworks here, your previous homework, so if you want to pick up your homework, you can pick it up. And so your whole homework is here. If you have questions about the material, I'm going to be in my office. Yeah, and I'm going to post a new homework today, but that one's going to be due Wednesday after the Thanksgiving break.
Did you say the final is not an option?
The final is optional, depending if you want to take it.
Okay. Thank you.
But the final is not the third exam.
Yeah. I'll still get 1 point.
Yeah. Thank you.
Thank you.
Thank you.
Is the final optional or mandatory?
The final is optional, so we still have one more part. Okay? Thank you.
Is there only one?
Only one homework, yes.
And is the final cumulative or?
The final is cumulative.
Are we gonna have a good review for it?
Yeah, I mean, if you decided to take it, we can plan on a review.
Oh, you can decide?
On the final? Yes.
Oh.
Yeah. So I think I need to explain this one more time. We have a third partial, which is the third exam for the class.
Yeah.
That will be the week, the 5th of December, December the 5th. Then we also have a final which is optional. So you decide if you want to take it or not. You can refer back to your syllabus and see how the percentage will change if you decide to take the final or not.
December 4th, right? December 4th.
December 5th is the third exam. The final is the 12th. Optional.
That's my birthday, though. So.
Today's my birthday.
Oh, happy birthday.
Thank you.
I get a birthday present. Hey, here you go. Oh, yeah.
I still got
There you go.
I got 86, 87.
I'm not sure where my homework is, but.
The homework is 10%. Yes. Homeworks and lab together are 10%.
And do you give that grade like before?
Yes, you will have your grade before making the decision. So I'll let you know your grade up to that point, and then you decide if you want to take the final.
Thank you.
I just want to.
Yes.
I mean, it's really nothing. I don't really care for the 2 points like that, right? But when I was doing this, I just want to know like how I got that one wrong.
So, how,
6.300. Or maybe we can look at the solution. I think it will be easier. So that's 6.58. Okay. So for this one, you needed to use the gamma. So you're looking for the same probability. This is correct. But you're using the exponential. Wait, how do you define x? We need to look at the exercise description. We have the textbook here. This. Yes, sir.
yeah, I didn't mean to send you that email so late, but
Yeah.
where I was, I don't know, I put, I'll work on it early,